Hi everybody, welcome back to the channel. In this video we're going to take a look at some practical applications of vectors, including one example dealing with forces in physics, and then two examples using a dot product and seeing some applications of a dot product. So let's start out with the first example involving forces. Let's suppose that we have an object that is being pulled by two different forces. Think about something kind of being pulled in two different directions. So two forces, we're going to call them F1 and F2, are both pulling on an object, and F1 has a specific magnitude, or again, think length. So two forces, F1 and F2, are pulling on an object, and we know their magnitudes. F1 has a magnitude of 10, so here's our language or notation for the magnitude. Kind of looks like an absolute value. And then the magnitude of force 2 is going to be 20. Okay, and here's the picture that's going to go along with this. So I want you to use this picture as kind of a guide. Here is one force right there, and then here is the other force right there. And before we get too far, I could ask a question like, which of these forces, which of the forces is represented by which of the vectors that are drawn here? And so hopefully it's pretty clear that this is force 1 because that's shorter, and here is force 2 because it's longer. And remember, the longer forces, or the stronger force is going to have a larger magnitude. Okay, so we need to have some angles in here as well. This force 2 has an angle of 150 degrees. That's kind of like its direction, which is like our theta when we talked about polar coordinates, and F1 has an angle of 45 degrees. So I'm going to write force 1 like this. I'm going to write it as force 1 equals 10 times the cosine of 45 degrees. Don't know what happened to my force 2 there. Plus, or I should say comma, because we're not using IJ notation here, comma 10 sine of 45 degrees. Because remember from our polar coordinate formulas, r cosine of theta was your x coordinate and r sine of theta was your y coordinate. And then you could write F2 as well, very similarly to this. It would look something like 20 cosine of 150 degrees, comma 20 sine of 150 degrees. So that's one of a couple of different ways you could write these two vectors. And the question is, where is this object going to end up? So this object is getting pulled strongly in the F2 direction, but it's also getting pulled in the F1 direction, not quite as strongly, but that still matters as well. Where's the object going to end up here? And really where the object is going to end up, and this is why we talk about combining vectors together. Let me put it in a different color over here. The object is actually going to end up somewhere over here, because it's getting pulled more in the F2 direction than it is in the F1 direction because of the stronger force, but it's going to be somewhere in between those. In fact, if you were to think about kind of copying and pasting this vector over here, there's your F1 vector. Remember, it doesn't have to start at the origin. Or another way to think about that is, if you look at where the F1 vector is, and then from F1 go out to and draw the F2 vector, they all end up in the same spot. So the vector that we have in green, kind of in the middle here, this vector right here is actually F1 plus F2. Okay, and so this is actually plus F1 plus F2, and since I can't write in bold, I'm going to go ahead and put little arrow markers above my F's over here to say that they're vectors. And so the question is, what does that look like? Well, if you take these two vectors and add them together, by the way, you know what the cosine of 45 degrees and the sine of 45 degrees and the cosine of 150 and the sine of 150 are, you can add those together. So your result here, so your resultant location of where is this object going to end up, looks like taking, let's see, cosine of 45 is root 2 over 2, sine of 45 is root 2 over 2. So you can take your x coordinates and add them together, and your y coordinates and add them together. This is going to look something like 10 root 2 over 2 plus 20 times, let's see, what do we have there? The cosine of 150 degrees. So what is that? That's a negative root 3 over 2. It's like your 30-degree angle in quadrant 2. So this is the x-coordinate of your result, and then the y-coordinate, if we go back, would look like 10 root 2 over 2 and then plus your y coordinate over here, which is 20 times the sine of 150. The sine of 150 is like your 30-degree angle in quadrant 2, but the sine is positive in quadrant 2, and this would be your resulting vector. Now, obviously, you could simplify this a little bit. 10 and the 2 can cancel. You get 5 root 2, let's see, minus 10 root 3. That's your x-coordinate. And then 5 root 2 plus 10 as your y-coordinate. Okay, so this would be your result for where does that thing end up. Okay, let's go ahead and take a look at an application of the dot product. We found the dot product in my last video. You should have seen that in other places as well. One of the main applications that we're going to look at as far as finding a dot product is actually very, very similar. If you remember in trig, to something called the law of cosines, with the law of sines and law of cosines. One of the results that's really similar to the law of cosines for us is going to look something like this. If you take u dot v, this is actually equal to the magnitude of u times the magnitude of v times the cosine of theta, which is actually going to end up being the angle between those two. This almost is very, very similar to the law of cosines. And so what it actually ends up giving us is a formula for how to find the angle theta in between two vectors u and v. And we can look at it like this. The cosine of theta is equal to the magnitude, or is equal to u dot v divided by the magnitude of u times the magnitude of v. And remember, in the last video I told you that every time we do something, we want to be careful about, do we get a number or do we get a new vector? And so remember that when we take a dot product here, you get a number. When you take a magnitude, you get a number. When you take a magnitude, you get a number. So when you see this down here, I could put a dot there, I don't have to. That actually means a multiplication of two numbers. Down here, this is not a dot product of two vectors, because the magnitude of a vector is just a number, the magnitude of a vector is just a number. You're multiplying those magnitudes together. So you should get a number here when you do all of this. You get a number on top, two numbers on the bottom, multiply together. You get one number for the cosine of theta, and then you can find theta with that. Okay, so this is going to be a really big application for the dot product, because obviously it has a dot product in it in the numerator. And so I'm going to go ahead and put a box around here and say, hey, this is one you really, really need to know. This is one that's really important for us as far as being able to use this all the time. And by the way, this is going to be true when we get to three-dimensional vectors as well, because nothing is different with three-dimensional vectors. You are still going to find the magnitude of u in three-dimensional vectors the exact same way that you found it in 2 dimensions. You're still going to find a dot product in 3 dimensions exactly the same way you found it in 2 dimensions. So really nothing is different in 3 dimensions than we have in 2 dimensions. Let's take a look at an example of this. U looks like the vector 2, 5, and V looks like the vector 4, negative 3. Okay. And we could take a second and find the angle theta between the two. Again, by using that, we got to know the dot product of u dot v. So u dot v on the top is taking the dot product of two vectors, but we will find a number as a result, because remember, it looks like 2 times 4, the x-coordinates, plus 5 times negative 3. There's your dot product. And then the magnitude of u is the square root of 2 squared plus 5 squared. That's just essentially the Pythagorean theorem. And then the magnitude of v is the same thing, the square root of 4 squared plus a negative 3 squared. Doesn't really matter that it's a negative 3 because we're squaring it. It's going to become positive anyways. So on the top, let's see, we have 8 minus 15. So we actually get a negative 7 on the top. You might say, is that okay to get a negative? It is. Think about what we're going to do next at the end. We're going to probably take an inverse cosine. And remember, what does it mean when you have the inverse cosine of a negative number? This is why we got to remember that idea of which quadrant you're in. We talked about this a lot this semester. When you have an inverse cosine, remember it's restricted to these two quadrants over here. And so if you have a negative number that you're taking the inverse cosine of, then you should be getting an angle that's somewhere over here in quadrant 2. So that's something we should expect to see. But that's okay. All right, let's see. In the bottom, we have 4 plus 25 is the square root of 29. And then in the bottom here, we have 16 plus 9. That one's not unfamiliar to you. That's the square root of 25, which is going to end up being 5. So here's what we have so far. We have the cosine of theta is equal to negative 7 over 5 times the square root of 29. Now, some people would say you got to rationalize your denominator. Honestly, I don't really care. We're going to end up taking inverse cosine here anyways, and so it doesn't really matter what you type in your calculator. Your calculator doesn't care if you have a square root on the bottom. I don't really care anyways. So theta is the inverse cosine of negative 7 over 5 times the square root of 29. I don't recognize that one on your unit circle. So we should probably have to run to our calculator here, and I think what you'll find is something like 105.1 degrees. Again, this shouldn't surprise you here because we already knew we were supposed to get a quadrant 2 angle because we were taking the inverse cosine of a negative, and so again, that we should just be able to check our answer and say, does that make sense with what I thought I should have gotten? I hope so. Okay. All right, another practical application of a dot product is something that we call a component vector. And so here's a picture that I want to kind of start out with in this problem. Let's say we have a vector like this. And what we'd like to be able to do is, or I tell you what, maybe all right, let's take a look at another example. Something else that we can do with dot products is something called a component. And let's say we have a vector right here and we have another vector right here. Okay, and here's the idea of using a component. A lot of the times what's really helpful is to break down a vector into two vectors that are perpendicular to each other. Later on, we're going to use the word orthogonal instead of perpendicular. It's probably a new word for you. And so we're going to break this down into one vector in blue here and then the other one in blue, where that you get this vector u right here as being two vectors added together with each other where those two vectors are perpendicular. This is really common to be able to do something like this. All right, and to do this, we actually need a dot product because one of the vectors we're going to have, like if we have a u here and a v here, one of the vectors that we have is going to look like needing to use u dot v. So if you ever hear of something called a projection vector, this is the idea here, where if we have a projection vector, we are essentially projecting u onto v. Okay, now what this is going to look like is essentially trying to scale down the vector v and make it smaller so that kind of it becomes this one right here. We're trying to make it smaller so that we get this vector that's just kind of a mini v there, you almost might call it. And by the way, sometimes we could have a picture where v is small and u is big, and then what we'd actually be doing is we're trying to make v bigger and extend out to there so that we get a perpendicular. And I won't go into a ton of detail on this, but here's what the projection vector looks like, is a projection of u onto v looks like u dot v. Again, these are vectors, so you should expect to get a number on the top when you take their dot product, divided by v, the magnitude of v, I should say, squared. And so notice this whole thing right here should just be one big number, because it's a dot product on the top and a number on the bottom, and then multiply by the vector v. And what this fraction piece does is it scales v to either make it shorter, if that's what's needed, or like in this picture here, or to make v longer than if like in this picture right here. And so that vector, actually, this dot product helps to be able to scale v correctly so that we end up getting a vector that is perpendicular to another one there that gives you u. Okay, so I'm not going to go into every detail here, but I just want you to see kind of what is this doing. This dot product is helping us create this fraction that ends up being a number here that is going to scale v correctly, either make it bigger or shorter, so that we can have two vectors that are perpendicular that end up giving us u when we add them together. Okay, so there's a couple examples for you that use dot products and that use practical applications of vectors. Hope you've enjoyed.